Welcome to this 12th lecture in this physics of materials course, physics of materials series of lectures. In the last last few classes we looked at the Druid model for conductivity of metallic materials, and as I have mentioned, the model is more general. We have focused on conductivity. You can look at other properties and how they are predicted using the Druid model as well. So for example, there is prediction of optical properties and so on. So we have not really focused on that. We have picked up conductivity and thermal properties, thermal conductivity and electrical conductivity, and we saw its successes, we saw its failures, and in the last couple of classes we have been trying to narrow down on the reason for the failure, because that is the way forward. We would like to understand, we start with a simple model, we would like to see why it has failed, and on that basis we would like to improvise on the model or improve the model, and if necessary try out a completely different model. As in the case with most things in science, we would like to settle down with the simplest explanation we can give for any phenomenon that we can see. So the simplest explanation you give, which completely adequately explains everything that you experience, is the explanation that we should go with. So this is the approach we wish to take. So in our search for the problem with the Druid model, what we sort of narrowed down to was that the manner in which the model predicts the distribution of energies in the system. Apparently there is some issue with that, because that is where the specific heat behavior begins to manifest itself. The manner in which those energies are there and the manner in which the system is able to absorb energy and so on. So something to do with the energy is an issue with this model, and also something to do with the way in which velocities are distributed within the system, which is again reflected in the way the energy is distributed in the system. So so this was something that we narrowed down to as the place which we should focus on to identify the source of problems with this model, right. Then we also looked at the fact that we are dealing with a very large system here, large in the sense that we may be still dealing with 1 meter cube, which by itself is not a very large piece of material when you think of it that way, because it is simply 1 meter by 1 meter by 1 meter. So that is something that we can physically visualize, but in terms of the number of particles that are present there, the number of atoms that are present there, and therefore the number of free electrons that are present there, we are looking at about 10 power 28 particles or free electrons. That number is a very large number. Okay, so when you look at energy of the system, the velocity distributions within the system and so on, when you have such a large system, it is not physically feasible for you to actually independently measure the velocities and energies of each of those particles and then somehow do an average. So therefore as we discussed in the last class, our approach is to do a statistical approach. Okay, so and in that sense we also looked at a few examples where we took a small amount of energy, some 3 energy levels, and we had 2 particles, 3 particles and 4 particles which we took, and we tried to populate those energy levels with those 4 particles, with those number of particles that we had, subject to some constraints, that the overall energy was fixed, the volume of the system was fixed, and of course the number of particles that we had chosen was fixed. From that analysis we concluded that as the number of particles increases, then there is something that we would call as the most probable microstate, and and we were able to extrapolate and say that as you reach very large numbers of particles, then of all the microstates available in the system, the most probable microstate is significantly more probable than all the other microstates combined. Okay, so that is the important thing, it is more probable than all the other microstates combined, not just more probable than the next most probable microstate. Okay, it is more probable than the next most, the next most and the next most all combined, and all the way up to 0. So you do all possible additions, one microstate stands out in a huge way in that calculation, and that microstate then becomes the most probable microstate, and it so significantly swarms the other microstates that when you take a snapshot of the system, you are more or less likely to find that system in that single microstate which happens to be the most probable microstate. Statistical mechanics takes advantage of this concept, or is based on this concept. It is the fundamental idea of statistical mechanics is if you have a set of rules which a large system is following, then you would based on the kinds of rules that the system is following, you may find situations where one microstate completely swarms all the other microstates. If that is the case, and in the kinds of systems that we are discussing that happens to be the case, if that happens to be the case, then the equilibrium state of the system is simply the most probable state of the system. All the other states of system states that are available to the system then become negligible, okay, negligible and non effectively not available for the system from a statistical point of view. So take a snapshot, you will find it in the most probable state. So this is the fundamental idea of statistical mechanics. So therefore we find that given our kind of system, the kinds of the sizes of the systems that we are dealing with, and this convenient and very useful concept of statistical mechanics, it makes sense to us that when we want to talk in terms of energy of the system, when we want to talk in terms of the velocity distributions in the system, then statistical mechanics is the tool that we should use, or the methodology that we should use to come up with the description for the system, okay. So therefore in our efforts to look at the energy distribution in the system and also the velocity distribution in the system, we will use the statistical mechanical approach, and more specifically for the kind of particles that we have chosen, which we described as identical but distinguishable, okay. When you have a combination like that, identical and distinguishable, the statistics for such a set of particles, a large collection of identical but distinguishable particles, has been worked out, and it has been worked out, the credit for this is given to Maxwell and Boltzmann. So there is a statistical mechanical approach called the Maxwell, which results in the statistics known as the Maxwell-Boltzmann statistics, which is applicable to the kind of system that we have described, which is an ideal gas system, and therefore has been imposed also on the collection of electrons that we have. So when we look at the Druid model, the concept we should be alert to is that in the Druid model, Maxwell-Boltzmann statistics have been imposed on those electrons, or it is assumed that the electrons follow the Maxwell-Boltzmann statistics. So that assumption has been made, it is not stated upfront to you, but the moment we say that we have taken ideal gas rules and ideal gas behavior and imposed it on the electrons, or assumed that the electrons behave like ideal gas molecules, effectively we have also assumed that the electrons in the solid obey Maxwell-Boltzmann statistics, okay. So this is the key here. So what we will do today is to derive the Maxwell-Boltzmann statistics, okay. We will derive the Maxwell-Boltzmann statistics, and this will lead us in fact to further discussions later, because it will enable us to better appreciate what alternate statistics can be used when you look at a bunch of electrons. So first we will see what we have already done, which is the Maxwell-Boltzmann statistics. We have imposed it already on our system, so we are merely going to look at what we have done effectively, even though we have done it without openly saying it. We have actually effectively imposed the Maxwell-Boltzmann statistics. So we will derive that today, and in subsequent classes when we look at, we give new characteristics to our particles. We will say that no, our particles are no longer going to have certain properties, they are going to have certain other properties. When they have certain other properties, there is an other statistical mechanical derived statistics which would be appropriate for them. Then we will impose the other statistics on these particles, then the predictions will change, and at that point we will see if those new predictions are any better than the predictions we have currently made, okay. So with this kind of an introduction, we will now actually derive the Maxwell-Boltzmann statistics. So that is what we will do today. So in our system we are saying that first of all it consists of identical but distinguishable particles. I mentioned this in the last class, and I will alert you to it again. These are very important words which when stated in a conversational sense probably conveys something to you, but when it is stated from the perspective of statistics, the perspective of behavior of particles, what they will do, what you can expect them to do, what you can expect them not to do, and therefore make predictions on collections of large collections of particles, these are very important words. And in our very next class we will spend a significant amount of time specifically exploring what these words mean, what possibilities we have, what possibilities we have with respect to these two words, and what are all those possibilities going to mean. So that we will do in the next class. for the moment you just assume we will just accept these words as they are and proceed with the derivation. Okay, so we have a large collection of identical but distinguishable particles. Okay, so this is what we have. So we will just say the total number of particles in our system is n. We will say the volume of the system, total volume of the system is fixed, and let us say that U, capital U is the total amount of energy. Okay, total amount of energy available in the system. So these are fixed, these are constants so to speak for our system. Okay, so and I mentioned again last class the importance of V being constant for theoretical studies, because then that fixes the energy levels that are available in the system. That again, that itself is a concept we will just accept on face value for now. Later on in our course we will actually convince ourselves in a more detailed manner that that is the case. Okay, so for now you just accept that this is the case, it is a confined system so to speak. Total number of particles is fixed, total volume is fixed, total amount of energy is fixed for our system, right. So with this with these constraints we are going to derive the Maxwell Boltzmann statistics. Okay, so this is what we are going to do. So to do this we will make some more assumptions about the details of our system. So what we will say is that in the system, see we are saying upfront that you have a large collection of particles, there is a total energy, there is a total temperature associated with the system and so on, and there is a distribution within the system. Okay, so this is what we seek. We wish to know if there is a range of energies available within the system, how many particles are at each energy level. So when we talk of distribution, that is basically what we are looking at. So you have very small amounts of energy, very large amounts of energy available in a scale of energy, and then you may have a very tiny amount of particles at the small lower levels of energy, tiny amount of particles at some other energy level, or for example we just do not know that this is the case, and we may have some other some energy levels which have high numbers of particles. So when you take an average you have to look at the number average of the energy, and then that will give you the energy of the system so to speak, right. So times the number of particles will give you the energy of the system. So we realize upfront that the information we seek when we look at this kind of a system is how many particles or what fraction of particles is sitting at what energy level is the basic information we seek. Once we have that, we have all the other information so to speak. Okay, so we will get all the other information from it, where the velocity distribution will also come related to this information. So although our total number of particles is fixed, what we have within the system, total energy is fixed. We have let us say within the system we have energy levels epsilon 0, epsilon 1, epsilon 2, epsilon 3, and epsilon r. These are energy levels available within the system. Okay. So this is fixed for the system because we have said it is a constant volume system and so on. So these are all fixed values of energy. So there is nothing that is changing about them, we just have these energy levels. Now at each of these energy levels what we do not know is how many particles are sitting at these energy levels. That is an information that we do not know. Okay. So for example we will just say upfront we do not know, so we will just say that there are n0 particles sitting at E0, energy level E0, N1 particles sitting at energy level E1, N2 particles sitting at energy level E2, N3 sitting at E3, and so on till we have Nr particles sitting at energy level Er. So this arrow is simply to show you that which energy level they are sitting at, right. So we have N0 particles at E0, N1 at E1, N2 at E2, N3 at E3, and so on till we have Nr at Er. We would like to get a sense of what are these values N0, N1, N2, N3 and so on, or what is the fraction of them, I mean as a fraction of the total number of particles. So that is the information that we seek. So in our system if you see, many things are sitting constant, only these are the numbers that can change, okay, only N0, N1, N2, N3, N4 and so on till Nr, those are the things that can change. Even this is fixed, the energy levels E0, E1, E2, E3, E4 up to Er, they are all fixed values, there is no flexibility in it, they are all fixed. So only this can change, right. So this is what we wish to find out, this what are these numbers, right. So what we said is that the equilibrium state of the system, we want these numbers in the equilibrium state of the system. When the system has reached an equilibrium, what are these numbers we wish to know. So the equilibrium state of the system is one which is the most probable microstate of the system, okay. So that is again something that the statistical mechanics tells us, and we are assuming that the system is following all those rules, right. So if you look at, if you now have a given set of N0, N1, N2, N3, N4 and so on up to Nr, okay. So let us just say we have one example of this collection, now we would like to know in how many ways we can get this N0 to be what it is, N1 to be what it is and so on. So the way that would occur is the number of microstates, we will call that omega, number of ways of attaining this microstate, attaining a given microstate, okay, and I will just put down the formula for it, then we will discuss what it is. Omega is n factorial divided by n0 factorial times n1 factorial times n2 factorial times n3 factorial and so on times nr factorial, okay. So this is capital omega, which is the number of ways in which you can attain this particular microstate. As I mentioned, everything in the system is constant, including E0, E1, E2, E3, E4, Er, they are all fixed. We only have a choice of what is the actual value of N0, what is the actual value of N1, N2, N3 and so on Nr. So for a given microstate we can have specific values of N0, N1, N2, N3 and so on, but if you choose an other microstate those numbers would change, okay. So they are not for a given microstate they are fixed. If we want to, when I do this calculation for a microstate they are fixed, then when I can do the same calculation for another microstate where say N0, maybe 2 particles have been added to N0 and those 2 particles have been removed from N1. So in the new microstate this would be N0 plus 2, that would be N1 minus 2, everything else would be the same. So like this you can keep on adding particles, removing particles from different energy levels, and for each possibility that you have you can calculate the number of ways of attaining that particular microstate, okay. So in this example, as I said, we have n factorial by n0 factorial, n1 factorial, n2 factorial and so on. If as I mentioned, if I removed 2 particles from n1 and added them to n0, the same calculation would have n factorial on top, it will have n0 plus 2 factorial, n1 minus 2 factorial and everything else would be the same, okay. So this is the way in which you would come up with the number of ways in which you could attain a single microstate, a single combination or a single set of n0, n1, n2, n3, n4 till nr. Now also in terms of the way in which this equation is been written up, it is the same as saying in how many ways can you arrange n particles, which is the total number of particles in the system, such that n0 are of one kind, n1 are of one kind, n2 are of another kind, n3 are of another kind, nr are of another kind. Then you would come up with a formula like this. What is the other kind here? They are all identical and distinguishable. So what do we mean by other kind? Simply that they are at a different energy level. These N0 happen to be at E0 energy level, so they are of one kind, so to speak. So n1 happens to be at E1, so they are of another kind. So that is how we, if you want to compare it with something that you have done in high school math, that is how you would come up with this. So this is the ways in which number of ways of attaining a given microstate. So now our problem is simple. So we have now taken a very large system, and from that system we have actually come up with a formula which tells us the number of ways of attaining a given microstate in that system, right. So this is a very useful piece of information for us. What we need to know is what is that combination of n0, n1, n2, n3, n4 till nr, what is that particular combination which maximizes the value of omega, okay. So that is all we seek to know what is that combination of n0, n1, n2, n3, n4 up to nr which maximizes the value of omega. That particular combination which maximizes the value of omega then results in the in that microstate becoming the most probable microstate, right. We said upfront that if it is the most probable microstate, that is the equilibrium state, because it will swamp all other states combined. So therefore if we actually look at this, if there is any way in which you can find out the set which maximizes this omega, that is the set that you are interested in. The moment you know that information, you know the distribution, then you know that for that particular set some value, I will just give you some arbitrary value, maybe 21, n0 is 21, maybe n1 is 5000 something. So you have 21 particles at E0, you have 5000 particles at E1, that is the equilibrium state of the system. From there you can get velocity distribution, everything you can get from there, right. So that is just arbitrary numbers I have thrown in there just to give you some feel for what we are talking here. So so our purpose is therefore to maximize this, right. So this is what we wish to do. So to do that we will do some we will make use of mathematical tools which are of convenience to us. So what we will do first of all is write instead of dealing with omega directly, we will deal with ln omega. So quite simply this is simply ln n factorial minus incidentally, okay, if we go back here we can just to use a mathematical notation, this is the same as n factorial divided by pi of I equal to 0 to I equal to r n I factorial. Just as we write sigma for sum, we write pi for a product, okay. So just as we write sigma I equal to 0 to I equal to r of some bunch of terms, so the same way if in this case it is a product of all these factorials n0, n1, n2, n3, n4, n5 up to nr, so that product is represented by a pi instead of a sigma. So this is what this compact notation is. So this compact notation we will now write here, you have ln n factorial up there minus, so the bottom you actually in the denominator we had a product of a whole bunch of terms. So if you take the logarithmic the log of it, the natural logarithmic of it, it would now be a sum of all those terms, okay. So natural log of all those terms. So therefore we have minus sigma I equal to 0 to I equal to r ln ni factorial. Okay, so this is what we have. So we now what why we choose ln omega is if you look at the behavior of omega and ln omega, they behave similarly in the sense that anything that maximizes omega also maximizes ln omega. So in that sense they are comparable, and therefore if you find a way of maximizing ln omega, that combination which maximizes ln omega will also automatically maximize omega. So therefore, and mathematically this is more convenient to use, that is all, that is the reason why we go with the natural logarithm of the omega. So now if you look at this we can rewrite this, we will make use of Stirling's approximation. So Stirling's approximation is a way of approximating for log of a factorial, okay. So what it basically says is that it basically says that ln x factorial is simply x ln x minus x, okay. So ln of some numbers factorial is simply x ln that number times the natural logarithm of the same number minus that number, okay. So this is all it means, and it turns out that this is actually a very good approximation. Even if you cross small numbers, you cross even 10 or something like that, or some 10, 20 things like that, small numbers you cross, this you will find if you just run the calculation, you will find that these numbers work out very close. Okay, so you do not have to go to a very large number before it starts working out well, but and it is intended at aimed at large numbers, at large values of x, but it turns out that even at small values of x this approximation holds true, relatively small values. I mean when you talk 20, 30 and all, those are all relatively small numbers, it holds true. We are looking at a system again, as we have mentioned many times, 10 power 28 particles. So obviously this if you have any split up of it, chances are you are well past this approximation, well past the range where above which the this approximation holds. So therefore this approximation is fine. So the minimum range we would already crossed, and therefore we will be this approximation would be valid. So with this approximation we will rewrite this formula here. So therefore ln omega is now n ln n minus n minus sigma I equal to 0 to I equal to r ni ln ni minus ni. Okay. So this is the formula we have. Now we want to maximize this, right. So essentially we would like to do del ln omega by del ni is effectively what we want to do, but what it also means that is that del ln omega and that should be 0 if you have reached a maximum, if you differentiate it with respect to ni, which is that the only variable here is ni, right, that is the only thing you can change. N is also fixed, even though you have to keep track of that. In this formula n is fixed, so this value n here is fixed, ln n, this n, ln n, n, these are all fixed values, you do not have a choice, only ni can change. So effectively del ln omega by del ni, or if you just want to put it as del ln omega, it should be equal to 0. So if you look at del ln omega, that will this if you differentiate this with respect to ni, it is going to be 0 anyway because it is all constant. So this is simply minus del ni ln ni plus ni into 1 by ni into del ln ni minus del ln ni, okay, and this is going to be 0. So this is 0, right. So if you look at it, actually if you look at this term, this ni and ni will get cancelled, and that would leave you with del ni. So plus del ni minus del ni, so this will also get cancelled, okay. So this entire term gets cancelled. So this being equal to 0, which is what we are going to have if you are trying to maximize omega, will simply be imply sigma I equal to 0 to I equal to r del ni ln ni, the sum of del ni ln ni I equal to 0 to I equal to r is equal to 0. Actually there is a minus sign here, but since it is equal to 0 it does not really matter, you have del ni ln ni equals 0, that is the sum of those terms is equal to 0, right. So in our attempt to maximize ln omega, we find that we have run into one equation, del ni ln ni equal to 0. So we will make use of this equation, right. So our equation now, I will just put that down here, is sigma of I equal to 0 to I equal to r del ni ln ni equals 0, right. Now we started off by saying that the total number of particles in the system is fixed, which is why and therefore n is fixed, n equals constant, right. We said n is equal to constant, but ni is not equal to constant, right. So because in that all those energy levels, for the I energy level, I mean r energy levels that you have, you are going to move particles from one energy level to another and so on. So you have that freedom available to you. So at a given point in time you do not know, I mean you at a given instant maybe you may have a value of ni, but it is not fixed for the system, it is a variable, but the total number of particles is fixed. So therefore if you remove a few particles from any one energy level, you have to put that many number of particles into all the other energy levels put together, combined. Okay, so if it remove from one energy level, if you have removed 10 particles, then those 10 particles have to sit in have to be spread out across all the other energy levels. You cannot just remove it from the system altogether, right. So similarly, if you add 10 particles into an energy level, it has to come from within the system, you cannot just get it from somewhere. So n is a constant, therefore the sum of so this is, which basically means this implies sigma I equal to 0 to I equal to r of ni is what this n is, equals n equals constant, right. So this is what, when we say n is equal to constant, the sum of all the particles available in all the energy levels is a constant. So that is what we mean, which simply implies that any changes that you make in this I, which is you remove some particles from one, you have to put it somewhere else. So this implies that sigma over I del ni equals 0. So in other words, the total number of changes that you can make has to sum up to 0. You remove 10 particles, you have to add 10 particles somewhere, you cannot remove particles from the system. So n being a constant means that the sum of all the changes has to total up to 0, right. So that is what that equation is. So we have a second equation available for us, and then finally we have one more thing that we have constant, that is the total energy of the system is fixed. This implies sum over I equal to 0, I equal to r, epsilon I ni. This is the energy level epsilon I, there are ni particles in it, therefore the total contribution of the particles that are sitting at that energy level is simply ni times epsilon I, and you have a whole bunch of energy levels, I equals 0 to 1 to 2, 3, 4, 5, 6 up to r. So the sum of them, the sum of all the energy levels times the number of particles that are sitting in those energy levels is a constant, which is the total energy. So we will call it U equals constant. The energy levels themselves are fixed, there you do not have any flexibility, but ni can change, so that number of particles in that energy level can change. Therefore this implies that if you add particles or remove particles from any given energy level and put it out, those particles are then put into other energy levels, the sum of all those changes should work out to 0 in terms of energy associated with those changes. Okay, so in other words, if you differentiate this, what we are basically saying is sigma over I equal to 0, I equal to r, epsilon I del ni should equal 0, essentially differentiating this with respect to ni. If you do that, it will work out to 0, and the physical significance of it is simply if you remove 5 particles from one energy level and you distribute them into 5 other energy levels, then the total gain in energy of the system should equal the total loss of energy in the system. Therefore the sum of changes in energy in the system should be 0. So we have an equation here. So we have 3 equations here, this is 1, this is 2, and this is 3. Okay. So one way of describing the situation we have now is that this is the equation that we were trying to maximize in our attempt to maximize the find the maximum the microstate with the maximum number of ways in which it can be attained. We got this equation. Okay. So our attempt to get us the most probable microstate got us this equation, but that attempt is subject to these 2 constraints. Okay, the 2 constraints being total energy, total number of particles in the system is conserved, so cannot be, you cannot raise the number of particles or decrease the number of particles. Total energy in the system is also conserved, so you cannot raise the energy of the system or decrease the energy of the system. So we are trying to maximize a function subject to these 2 constraints. Now in the mathematics that you would have learned, we have learnt of maximizing functions and minimizing functions and so on, so that is something you are already familiar with. But we have added a slight twist here, which is the fact that we have 2 constraints on that system. The physical way in which people describe this kind of a situation is something like this. Let us say you are on a, if you want to look at an analogy from say geography, so you have some kind of a terrain. Okay, so you have a terrain, maybe you have a mountain side or something that you are walking along. normally when we talk of maximum and minimum of a function, it is like saying that what is the highest point in the mountain or and what is the lowest point in that terrain, okay. So that is the maximum and the minimum, but the fact that we have these two constraints is equivalent to saying that I do not want to know the point which has the maximum height in the mountain or the minimum height in the mountain. What I want to know is, in this mountain I first of all ask you to walk only along a particular path, okay. So you have a big mountain, but I am asking you to walk along a particular path which may not go all the way to the top of the mountain, it is an arbitrary path that I have determined. I am giving you some constraints saying you walk along this path only. In this path which is on that mountain, what is the highest point, what is the lowest point? That is the question that I want you to answer. I mean it is different from saying which is the highest point in the mountain and which is the lowest point in the mountain. The question is very specific. On this mountain, so it is not some arbitrary location, on this particular mountain you have a particular path that you have been assigned to, which may or may not take you to the highest point in the mountain, but regardless of where it takes you, in that path what is the highest point, what is the lowest point, that is what we are looking at. So it is the same as saying that you have a function which you want to maximize, but you are subject to this path given by these constraints. So you are stuck to that particular path that these constraints give you. Within that constraints, what is the maximum value that you are going to get? That is the question that we are trying to answer. So this is the mathematical problem that we are dealing with, right. So we will just rewrite only the final equations, then it will follow the method that we are using, which is sigma over I right. So we have three equations that we wish to solve. The mathematical method that is used to deal with this kind of a situation where you are trying to maximize one function subject to certain other constraints, the mathematical approach taken for this is referred to as the Lagrange method of undetermined multipliers. Okay, so the mathematical method that is used for this purpose is referred to as the Lagrange method of undetermined multipliers. Incidentally, what we have done so far is the same methodology that we will use for two other statistical configurations that we will consider later in the course. So you will see these things show up, this kind of an approach show up later also, but the rules the system will follow will be somewhat different, and therefore the results will be quite different. But the concepts we will use, the approximations we are using, this method of undetermined multipliers that we are using, all those things will keep showing up again and again. Okay, so this is called the Lagrange method of undetermined multipliers. So you can look this up in a mathematical book, in a book on graduate school engineering mathematics, but we will use it, and so to that degree we will even explain it here. So the basic idea is, when you have a situation like this, one way of solving it is what this Lagrange method of undetermined multipliers is to simply say that we will, first of all, we have three separate equations, so we will first combine these three equations, and before doing that what we will do is we will do this undetermined multiplication, okay, so to speak. So in other words, what we will do is we will multiply this equation by alpha where we do not know the value of alpha, okay. So we will arbitrarily multiply this equation by alpha, we will arbitrarily multiply this equation by beta, then we will add them, and the idea is that so we will first do that. Let's write that equation down where we have multiplied this by alpha and we have multiplied this by beta, which the values of which we do not know at this point, and therefore those alpha and beta are called undetermined multipliers because at this stage they are not determined, okay. So that is where this term comes from, undetermined multiplier. We have arbitrarily multiplied by alpha and arbitrarily multiplied by beta. So therefore we have I will just write it down, then we will discuss this in a moment. Ln ni plus alpha plus beta epsilon I del ni equals 0. right. So these 3 are all equal to 0, so if you just multiply this by a constant, multiply this by some constant, and then you add them, then they are all anyway going to remain at 0. So that we have done. So all I have done is I have taken this del ni out common, so del ni will come out, you will have only ln ni, this is alpha del ni because I multiplied this by alpha and I pulled out del ni which is out here, so I have alpha here, and you have beta epsilon I del ni in this equation, again I pulled out del ni, so you have beta epsilon I here. So this is what we get. Now the point is this sum has to be 0, right. Now the logic behind this process is based on this idea that this sum has to be 0 regardless of the value of del ni, right, because as we said in the beginning this del ni are variable, I mean is a variable, you can change the at a given because from I goes from 0 to I equal to r. In this system as we try to maximize the I mean look for the condition that maximizes the microstate, we are going to try various values of ni, and so at a given point in time we do not have control on exactly what each ni is going to be, each del ni is going to be, right. So you are going to try changes where you are going to add some particles here, you are going to remove some particles there and so on. So this has to be, this sum has to work out to 0 regardless of the actual choice of the del ni, okay. So that is when you have actually satisfied this the requirement, because to begin with we do not have control on the del ni effectively, right, we do not have control in the sense that we I will put it this way, we have a lot of choice in what the del ni can be. Therefore for the sum to be to guarantee that the sum to be has to be a 0, we have to actually, what we are actually requiring is that this term be 0. For this entire term to be 0, recognizing the fact that we have a lot of choice on del ni, and therefore only accidentally it would become 0 if you are depending on del ni to make it 0. For you to guarantee that it becomes 0, this term that precedes the del ni, that is what should become 0, okay. So this method uses this basic idea that when you have these constraints, if you multiply them and put them all into, multiply them by constants and add them all together, then you have sort of brought all the constraints into a single equation where you are now able to remove the variable and try to make it independent of changes on those variables, okay. So therefore this now is now required to be 0. So this is the general idea of the Lagrange method of undetermined multipliers, and like I said you can read this up more in a mathematics book, but this is what they will explain to you also, okay. So therefore we now require this to be 0, right. So we now have changed this entire mathematics to say therefore ln ni plus alpha plus beta epsilon I should equal 0. Now suddenly notice we have removed the sum, okay, the sum is no longer relevant to us, regardless of the value of del ni it has to be 0, therefore this has to become 0, okay. So that is what this becomes, all these preceding terms have to become 0, only then regardless of the del ni for all the possible values of del ni the final sum will always be 0 because the term that precedes it is always 0. So this is what we have, therefore we can now write, if you simply move alpha that side, beta epsilon that side, they will both be negative, and we just convert this to so ni will be e power all of these things. So therefore ni equals e power minus alpha and e power minus beta epsilon I, fine. So we are now getting very close to what we want. We have now ni, which is the number of particles in the ith energy level, okay, which is what we are really looking at. We may convert that to a fraction, in fact that is basically all that we are going to do, we are just going to convert this each of this into a fraction just for our convenience sake, but we now have it in terms of some alpha which we do not know yet and some beta that we do not know yet, but these are some constants, and but more importantly you have energy here. So in terms of energy we have the number of particles, if you have an energy level I can tell you what is the number of particles that are available at that energy level, right, and that is the information we want, and this is not some arbitrary number, it is the number that corresponds to the most probable microstate. We started all this calculation, we have done all these calculations with our very first equation being that del ni ln ni equals 0, that sum of that equation is the equation that maximizes the microstates, the number of ways in which you can get the microstate, okay, or corresponds to the most probable microstate. So therefore from there when you start and you come up with a value for ni, this ni ei combination for all the values of I that you can get will then also give you the most probable microstate, the distribution that corresponds to the most probable microstate, fine. So we will now just do some minor modifications on this Alright, so our equation finally works out to Ni equals e power minus alpha e to the power minus beta epsilon I, fine. So what we will do is now we will just try and make this in a form that is more convenient for us or more useful to us. So we will just take advantage of the fact that sum of all the Ni should equal the total number of particles. This is simply the number of particles at a given energy level. We have r energy levels, so if you sum up all the particles you should get the total number of particles in the system, which is anyway fixed. So this implies this is anyway a constant, so this is when we say sigma Ni, this means sigma of this term here because they are the same, and in this term this is a constant, there is nothing that is changing here, so effectively it is only Ei that is in that sum. So therefore it means e power minus alpha sigma I equal to 0 to I equal to r e to the power minus beta epsilon I equals n, right. So this is, and that n is a constant now, n is the total number of particles. This alpha does not have any subscript I, so it is outside the sum, it is a constant effectively. Therefore e power minus alpha is simply n divided by this sum. Okay, this sum in the denominator is actually called by a term called the partition function. So it is this is the same as n by capital P, where P is the partition function. Okay, partition function. What it is, it simply is that, I mean I just stated it, I will just explain it in a moment. What it is going to do is it's actually, see if you look at the original expression here, for every Ni this term shows up, right, for every Ni. Now when I sum up for all of them, this which is the term that we are seeing here is simply the sum of that particular part of the Ni term, and in a way it is like the it is what actually that gives you the fraction. Okay, so that is effectively if you take for a given term in the numerator you will have only one of those Ei's, in the denominator you will have the sum, right. So we will which is what you have here, let's just put it back here and then we can see it clearly. Now that you have e power minus alpha is n by p, what we are basically saying is that Ni is simply n by p times e to the power minus beta epsilon I. So what we have here Ni, so we started with a expression for Ni, we took the sum for n, using that we simplified and we got e power minus alpha as n by p, which is simply n by this sum, and that n by p is what I have put back here. Instead of e power minus alpha I have put n by p here, e power minus beta epsilon I. This p here is the sum of this e power minus beta epsilon I for all the epsilon i's that are available to us, right. So it is in a way it is the one that sort of helps you come up with a fraction, so to speak, because this is now summed across all the energy states, this is for just this energy state. So this is how you get this equation. Okay, so that therefore it is called the partition function, it helps you get a sense of how the particles have been partitioned across all the energy levels, right. So and it turns out that this beta is simply 1 by kBt, it is a constant 1 by kBt, kb is the Boltzmann constant at a given temperature, therefore it works out to a fixed value. So therefore Ni is simply n over p e to the power minus Ei by kBt. So we now have a value for Ni, right. So what have we got here in by doing all the mathematics, we have now got a expression for Ni, which then tells us the number of particles that are available in the ith energy level in the microstate, that is the most probable microstate, and that is the information we were searching for right from the beginning. What is the most probable microstate? And when we say what is the most probable microstate, exactly in fact the question we are asking is, in that microstate how many particles are sitting at which energy level, because that is what defines the microstate, it is not some arbitrary thing. So we now have an expression for that, what is the number of particles which are sitting in the energy level Ei there, and in the and this whole expression has been derived for the most probable microstate. So this expression is then the Maxwell Boltzmann statistic expression, okay. So the Maxwell Boltzmann statistics actually gives you this expression. If you wish to look at it some more, what it basically says is that if you keep raising the energy level, the number of particles will exponentially come down, because you have minus epsilon I here, right, epsilon I as a negative in the e power minus epsilon I by kBt. So the higher this value goes, exponentially the number of particles at that energy level will decrease, right. So in fact if you want to make a plot of this function, you will simply see if you write the energy levels down, okay. So this is the number of particles and this is energy, and this is number of particles Ni, okay, and this would be N0, N1, so on. So I'll just put it, draw the diagram and then we can see. So at E0 we have N0 particles, at E1 we have N1 particles, some E2 is somewhere here, let us say, we have N2 particles and so on, and then we have some ER, we have NR particles, right. So this is what we have. So this is the distribution of Maxwell Boltzmann that Maxwell Boltzmann gives us. So Maxwell Boltzmann distribution is the manner in which particles are distributed across energy levels subject to the constraints that we have just discussed, and it shows you that the particles are distributed like this. So when we derive equations based on the assumption that we are using ideal gas laws, we are using that the particles are identical but distinguishable and they follow all the rules of ideal gas laws and so on, effectively the manner in which we are distributing energy amongst those particles is given by this distribution. The manner in which we give velocity is distributed, velocity and speeds are distributed across the particles will be a result of this distribution. It's from whatever we can calculate out of this distribution, that is the manner in which the velocities and so on will be distributed, and this is then directly reflected on the translational kinetic energy of those particles, average translation kinetic energy of the particles, the kinds of behavior they show with respect to specific heat. So if we make predictions for specific heat and energy of those particles, and it turns out that there is some problem there, then that problem translates to the fact that this distribution that we are seeing here is perhaps not applicable very well for electrons in a solid, okay. So this distribution of number of particles versus energy level is applicable very well for ideal gas particles which follow the ideal gas behavior, kinetic theory of gases, but apparently is not as appropriate for particles such as electrons in a solid, right. So we will in the next couple of classes, we will in the very next class we will actually look deeper into why this is not correct, and to do that specifically we will focus on those words identical and distinguishable and see what possibilities we have there, and how suitable the possibilities are for with respect to what electrons display to us, and then we will take it from there and see what might be a more appropriate way of doing it. And then eventually a few classes down the road we will actually at that point after the next class we will have to deviate a bit and look at some other background material, and then we will come back to a new statistical distribution which would then be more appropriate for electrons. At that stage we will come back to this distribution we have seen here and compare this distribution with the new distribution that we will come up with at a later stage, and see where is it that distribution gets it right and where is it that this distribution gets it wrong, and what is the problem that we have there, okay. So that is the direction in which we will head. So with this we will conclude today's class and take it up in the next class. Thank you.